The word electricity comes from the Greek word electron, meaning amber. Long before the discovery of the electron, Benjamin Franklin observed these effects and categorized charge into two types, positive and negative. This behavior follows the Lehrer rule. Like charges push apart, or repel, while reverse charges attract. How a material handles this charge determines its category. A plastic comb holds a static charge. Because plastic is an insulator, the electrons stay trapped where they were deposited. A metal comb acts as a conductor, letting those same electrons slide through the material and your hand to reach the earth. This process is a transfer, not a creation. Rubbing a rod with silk moves existing electrons from one to the other, meaning the total charge of the system remains constant. There is a physical limit to how small a charge can get. In 1912, Robert Millikan proved that electrical charge is not a continuous fluid, but a collection of discrete units. We express this through the formula Q equals NE. Charge functions like a stack of coins. You can have 1, 2, or a million, but you can never have a fraction of an electron. Every free charge is an exact multiple of the elementary charge, 1.6 times 10 to the negative 19th coulombs. We only perceive charge as a continuous flow in our daily lives because the value of a single electron is too small to detect without laboratory equipment. To calculate the interaction between these particles, we use Coulomb's law. It shows that the force is proportional to the charges and inversely proportional to the square of the distance between them. This electrical interaction is roughly 10 to the 39th power stronger than the gravitational pull between the same two particles. Many students overlook the square in the denominator. If you halve the distance between two charges, the 1/2 is squared, becoming 1/4. Mathematically, that 4 moves to the numerator, making the resulting force 4 times stronger than it was before. Because this follows an inverse square law, the force increases rapidly as charges approach each other. Small reductions in distance result in significant jumps in the physical push or pull. To understand how these forces act across a vacuum, Michael Faraday developed the concept of the electric field. By definition, the electric field is the force per unit positive test charge. Because a positive source will always repel that test charge, the field lines for a positive charge are drawn pushing outward radially. When a negative charge is introduced, the map changes. The lines exiting the positive charge now curve and flow directly into the negative charge, creating the visual structure of a dipole. These lines are mathematical tools. They show us the exact path any positive charge would take if placed within that field. When more than two charges interact, we apply the superposition principle. This states that the total force on a single charge is simply the sum of every individual force acting on it from the surrounding charges. However, because force has direction, you cannot add these like simple numbers. You must calculate the vector sum to find the net effect. Take a moment to try this. If you have 3 identical positive charges at the corners of an equilateral triangle, what is the direction and magnitude of the net force acting on the top charge? Repelled by the base, the top charge has 2 outward force factors at a 60-degree angle. Resolving them, horizontal components cancel out. Vertical components add together, leaving an upward net force of √3 times the individual force. The centroid net force is 0. Breaking diagonal forces into a standard grid allows you to solve for any number of charges, regardless of their geometric arrangement. Use this summary for your revision. D contains the quantization formula, Coulomb's law, and the constants for permittivity and elementary charge that you will use in every numerical problem. These laws of force and field lines are the building blocks for the next several chapters. Mastery here makes the study of magnetism, moving charges, and complex circuits much more predictable.